All right, so today we're looking at Stokes' theorem, which again lays the groundwork for a lot of big theorems out there and equations. One of them being justification for some Maxwell equations. So we'll hopefully get to those at the end. I do want to show you the one proof of a special case of Stokes' theorem because you guys are at the level where you can understand it, and so we should go through it. It is a little tedious, but I think worth it. So we'll go through a statement of it, the proof, one example, and then some applications. So first thing I want to draw your attention to before I even give you a formal statement of it is the connection to Green's theorem. So one way you can think about Stokes is that it's a higher dimensional form of Green's theorem. So one way to see this is to remember Green's theorem. What does it do? Well, it connects a double integral over a region D in the plane with the closed integral around the boundary of that region. So we take a region, double integral, and we evaluate the points at the boundary curve. That's roughly what Green's theorem did. What Stokes does is it takes it up a dimension. So we have a double integral of a surface and it relates it to either we can call it this delta S or some C, but this is a space curve of the boundary, and instead of the boundary of a region in the plane, it's the boundary of the surface, so it's a space curve traveling along the edge of a surface. So it really is just a higher dimensional form of Green's theorem. The surface kind of gives a normal vector, which gives us the orientation. For the space curve R. All right. But we're going to move into the formal statement of Stokes' theorem with all the caveats and things that need to be in place for it to apply right now. All right, so what does Stokes' theorem actually say? Well, if we've got a surface, all right, so there's some 3D surface floating in space here. We'll call this S. Around it is this boundary space curve. We can think of this as being some oriented space curve. We'll call that C. And so what this tells us is if S is, piecewise smooth, and it's bounded by this space curve C, which is piecewise smooth, which means, again, if it's just stitched together and all those pieces are smooth, they have nice derivatives. Smooth boundary curve C with positive orientation. Let's look at a vector field. Vector field whose components have continuous partial derivatives. Whose components have continuous partials in an open region that contains S. Then the statement says the line integral over the vector field of this curve is equal to the double integral over the surface of the curl of the vector field ds. Okay, so that's a statement of the theorem. So we're going to unpack a little bit later why the kind of curl gets involved, but what you can think of is if we're talking about the, let's see, the flow of the vector field through the surface, we're going to feel that at the boundary, right? And so if we walk around the curve, the space curve, this is going to tell us some important information about the flow through the whole surface. And we'll see a little bit why the boundary plays such an important role, and it's sometimes independent of the surface itself. So let's hop back to it here. So this may or may not look thematically similar. There is an analogy here between Green's theorem, Stokes' theorem, and the fundamental theorem of calculus, which is that we have, some integral of derivatives being mapped back and forth between values of f at the boundary. If you think of all the different statements of these theorems, this is kind of the theme between them all. If we add up all the change, it tells us something about the values at the boundary, and vice versa. If we have the values at the boundary, it tells us about the sum of all the changes. So another nice connection here is that Green's theorem is actually a special case of Stokes' theorem. You can think of this geometrically because what did Green's theorem do? Well, it related a double integral in the plane, all right, in the xy plane, to a curve, a boundary curve in 2D. Well, Stokes is doing this in 3D with surfaces. So obviously if we just project it down into the plane, then this is going to apply. So we see that this line integral through the vector field, if we follow Stokes' theorem, will give us this, the double integral of the curl of f over s. And we know that when it comes to our vector field for the curl, all of that is going to be living in the plane. So the normal vector is going to be just k hat, right? The z component, the upward z component. So that's how we know that this is really just in the xy plane with the normal equal to k hat. And so this is really just a special case of Stokes' theorem. Tells us how to evaluate Green's theorem. Okay. So what I'd like to do now, so we've seen a little bit of connections to things we already know. We've seen a diagram of what this looks like. I want to walk through the proof of where this comes from. We'll try to do it as carefully and quickly as possible, and then we'll move into an example with some applications. But I encourage you to, as best you can, follow along with this. This will not be something that I assess you on. You won't need to recreate this, but it is important that you understand where this comes from. All right, so let's assume that we've got all the caveats listed. We have a piecewise smooth surface, a piecewise smooth curve, and that our surface is given to us where the z is a function of x and y. This gives us our surface S. Okay, so again, I'm going to draw a little diagram so we can have something to reference. say we've got some surface S. It has a normal vector, n. It's got some smooth boundary curve, C. Again, that orientation is given by n's direction being upward. And it's sitting on top of, its projection in the plane. This is maybe some D region. And we know that it also has a boundary curve. We're going to call it C sub 1. Also in the mix, and maybe I'll duplicate this so it doesn't get all cluttered. But also in the mix is our vector field, right? So what's our vector field doing? Well, let's imagine it's got some, little vectors, little fluid flow happening everywhere. We're obviously most interested in what's happening through the surface and at the boundary. So this is kind of my F vector field in R3. Tells us where the particles want to move. All right, so since S is an explicit function, and you actually might want to have out our formulas from last class nearby for this so that you can reference them a little bit easier. And we're going to replace F with curl F. Remember that curl F is a vector field itself, right? And it talks about the tendency of the fluid flow to want to rotate about an axis. So if we replace F with this curl F vector field, then from one of the forms of the surface integrals last time, we said if it was a surface integral of a vector field, dot ds, then we're able to take the double integral over the region of that vector field, here it's curl F, dotted with negative z sub x, negative z sub y plus 1 dA. Right? So it's just a dot with each of these components. And so what do we get? Well, we got to remember what curl is. This was a little while ago. Right? And curl is for a three-dimensional vector field, it's, r sub y minus q sub z minus p sub z minus r sub x. And these should be plus, I believe, and then plus q sub x minus p sub y. And this is a vector, right? So this is I hat, j hat, k hat. So just to remember that, because that's going to come into play right here, where we substituted in for d. So these are going to become pretty big. So for curl, this gets dotted with the partial of z with respect to x. We're going to write dz dx minus p sub z minus r sub x, these partial derivatives dz dy, plus that last component of the curl, q sub x minus p sub y, all dA. All right, so we're going to mark this for later reference, because what we're going to do is show that the other side of this equation equals the same thing. All right, so we're going to mark this down as our reference point. And again, this is not how proofs are actually created, right? They're not done in this linear fashion. There's a lot of messiness, experimentation, and discovery. We're just kind of walking through the logical framework for it. And then each of these, partial derivatives, these are all being evaluated at x, y, g of x, y, because that's what our surface is given to us as, rather. So our next point here, if we know that x and y can be parametrized for some values of t for C1, which again, C1 is that boundary around our domain, or our little region in the plane here. So if we can parameterize C1 with x equals x of t, y equals y of t, then that means the surface and C, the boundary of that surface, is given by, well, can parameterize x and y with t, and then we let z be g of x of t, y of t. So what does that do? That takes this curve and shoots it up to C, and then it moves around the edge in a space curve. Space curve. All right. So we've got our boundary curve set, so now we're going to play with this equation and see what we can come up with. So therefore, this line integral of the vector field dr is equal to, well, the integral from a to b of p dx dt plus q dy dt plus r dz dt all dt. And this comes from our, again, our equation for line integrals through vector fields for explicit functions. So this is back a few sections. And so what we can do now is use the chain rule to unpack this a little bit further. And this is going to get pretty big relatively quickly. So it's the integral from a to b of, well, we got p dx dt plus q dy dt. Why do we have to use the chain rule? Well, z is really a function of x and y, right? So its derivatives have subderivatives. dz dt, we can use the chain rule here, plus r times, well, this would be dz dx dx dt, and these should be partials here. dz dx dx dt plus dz dy dy dt. Right, that's what we mean when we say dz dt in multivariate. So this is all in the integral. And so then with a little bit of shuffling, okay, so a little bit of algebra. I'm not going to go through all the steps of this part, but what we can do is reorder. We see that we've got some terms that have a dx dt, some terms that have a dy dt. And so we're going to rearrange this to be a little bit nicer. So we'll see that this is equal to p plus r dz dx times dx dt plus q plus r dz dy dy dt all dt. So what's cool about that is we can eliminate the parameter here by, quote unquote, distributing this dt and saying, well, this is really the integral over c1 of just p plus r dz dx dx plus q plus r dz dy dy. And then what do we have? Well, we have a line integral that's, a scalar dx plus a scalar dy. So we can actually apply Green's theorem here. So think about how Green's theorem would apply. Well, it relates the line integral through a vector field to the double integral of the region. And so we can rewrite this again. Oh, this should be a partial here. dz dy minus the partial with respect to y of p plus r dz dx all dA. Okay, so you can see how Green's theorem was applied there. Remember that each of these q, r, and p are functions. Let's say p, q, r are each functions of x, y, and z. Because to unpack this with the chain rule again is what's needed to map this back to our specially marked equation. Because this thing is going to be equal to the double integral over d of, so if I take the partial of q with respect to x, and the other note here, and z is a function of x, y. So in other words, I'll say this quickly, when I differentiate q, I'm going to have a partial with respect to x. The partial with respect to y will be 0, but then my z component's partial derivative will have a partial with respect to x. All right, so if I differentiate q with respect to x, I'll get a partial here, and the middle one will be 0 because there's no y, and then vice versa for y. All right. So when I take the partial of everything in here, what we're going to get will be q sub x plus q sub z, z sub x. And if I wrote this in Leibniz notation, which I'm not going to for the whole thing, but partial q with respect to z dz dx, okay, plus same thing for r sub x, where we had this partial with respect of z with respect to y. And so that's that first part here. Oh, and then the last bit, so partial of this with respect to x is, yes, r sub x, but r also has a z component which has a function of x, so it's going to be plus r sub z, z sub x, z sub y, plus r times d squared z dx dy, right? So this last piece here. And then that gets closed off. So that's just the first part. Second part, we do similar thing, differentiate but with respect to y. And so what do we get? Well, we get p sub y is z sub y, right? Because z is also a function of y, plus r sub y z sub x, plus r sub z, z sub y, z sub x, plus r, and then again this d squared z, that mixed partial at the end. And this is all dA. All right, so this whole thing's one big integral. What's nice is you'll see some stuff's going to cancel, right? Namely, this guy, this guy. We also lose this one and this one. And so what we're left with, q sub x plus q sub z, z sub x, plus r sub x z sub y minus p sub y minus p sub z sub y, and this guy, all dA. With a little bit of factoring, we can map this back to our previous. So if we take a look back, these two are equivalent with just a little bit of factoring, okay, grouping of terms. So what we've done is shown one side equals the other side. Therefore, we'll say, star equals star. Therefore, the line integral of the vector field around the boundary is equal to the double integral of the surface of the curl of f dot ds. So that's Stokes' theorem, okay, for when the surface is given as an explicit function, function of x, y. So this is a pretty powerful theorem. It was discovered / invented around the 1800s to 1850s. It's called Stokes' theorem. It's Stokes' theorem. It is attributed to Stokes, although it's somewhat contested. He was credited with finding this, but it was actually written to him in a letter as kind of like a challenge. It's also might be a fable or a false story, but he challenged his students to solve this problem. It's unknown if any of them did. But there are equivalent proofs for very, very similar theorems around the early 1800s. This is relatively new in terms of the math world. And as in this form that we see it today, it was really only written in like 1950. But what I found was interesting with the French and the Russians typically credit Riemann and Ostrogradsky with the first proof of this, whereas others attribute Green and Gauss for the preliminary forms, and then pretty much everybody points to Stokes. But anyway, there's just a little history behind this theorem and where it comes from. And then, so what I want to do now is show you an example of how we apply it in one direction. If you want to look in the book for applying it in the other direction, they're pretty well fleshed out. And then we'll talk briefly about some applications where this thing can take us. All right, so let's say we want to evaluate a line integral for a vector field when this is given by negative y squared I plus xj plus z squared k. And the boundary curve is the intersection of the plane and the cylinder, the infinite cylinder, x squared plus y squared equals 1. And we'll say that, it's oriented so that the boundary, this curve is the intersection, is counterclockwise from above. That's the positive orientation. So this is a okay line integral to evaluate, but a lot of times they are rather tricky to do. So what we can do is instead map it to the double integral of the surface of the curl of the vector field instead of going through the computation of the line integral. And the example I'm not going to show you is the other way around, when you would rather do the line integral instead of computing the curl and the surface integral. But we'll talk about why it's kind of what is interesting about this relationship in a second. So here it's easiest to do Stokes. So we're going to. So what does that mean? Well, we're going to need the curl of this vector field. And so I also wanted to do this to kind of refresh us on how we compute curl. Well, it's the cross product of the gradient, right? It's can also be thought of as this. So it's the cross product of d dx, d dy, d dz, and p, q, and r. So what this ends up being is 1 plus 2y k hat. Right, we get a few zero components in there. And so our curl vector, and it's a vector field, is given by 1 plus 2y k hat. Right. So let's go ahead and sketch out what this surface is. What's really happening here we've got a cylinder that's intersecting with this plane. So here's the plane y plus z equals 2. They intersected this curve. This is what we're calling C. And so what's interesting, and we kind of have to notice it here, is that the boundary is the only thing that really matters. This the surface inside the boundary can really be anything. And so there are many surfaces that can work. We don't need a question mark here. Many that can work. So we always will choose a convenient one. So in our case, why don't we stick with the plane, keeping it flat, and that it just intersects at this curve at the top, this elliptical space curve in space. So we can look and see, all right, well, this has got, a projection down in the xy plane of D. We know D is really the disk of radius 1 because of our boundary with the cylinder. And we know that up here for these points, at the height is going to be given by 2 minus y when we just solve that plane equation. So this line integral can be rewritten as, using Stokes, so this is the curl of f ds, which is really the double integral over d of 1 plus 2y dA. Why is that? Well, we're using this formula again, since z is a function of x and y, because it's equal to 2 minus y, we're able to use that form for a surface integral. And the partial derivatives with respect to x and y are both 0. And then we're left with, for f, and then we're left with just our k components. That's the 1 plus 2y dA. So why that's nice? Well, d is a circle, so that means we want to scoot to polar. So we've done this a few times. That means we're looking at the integral from 0 to 2 pi and 0 to 1 for r of 1 plus 2, not y, but instead r sine theta, r dr d theta. And then we're there. This works out to be pi. Okay, so again, what is this telling us? Well, it's telling us the value of the line integral of the vector field. So, what is the work done by this vector field on a particle moving along this curve? So that's equal to pi here. And so again, we used Stokes' theorem in the direction of, well, I'd rather evaluate the surface integral than the line integral. And I would say in general, that's probably the case, but not always. Okay, it depends on how hard the approach is for that. So just remember that you can use it in two directions. So now I want to just kind of explain a little bit some insight on the curl vector. So let's suppose for a second that C is a closed path, a boundary of a surface S, and V is a velocity field of fluid flow. Then the line integral of this velocity field we can rewrite as the dot product of V and the tangent vector with respect to arc length. And this comes back to this is 16.1 or 2. Remember that V dot T is the component of V in the direction of T, the tangent vector along the curve. So if we look at what that means geometrically, moving along this curve here on the boundary, which we'll call C, let's say I've got some point here and the fluid flow is telling me to go in this direction. Well, the tangent vector is something like this, and the fluid flow is in this direction. There is some positive dot product, right? Because they're pointing somewhat in the same direction. So here we can see that this would be positive because it is they're pointing somewhat in the same direction. Now, we have a similar situation. Again, we're moving around in this direction, and I'm looking at a particle here, and the fluid flow is moving this way, but my tangent vector is moving this way. Well, here we can say we know this is going to be negative because that dot product from here is negative. And if it's orthogonal, it's going to be 0. So if you have a vector field that's always orthogonal to your curve, then that's going to be 0. But what we call this integral the tendency of the fluid to move around the curve C. So we call it the circulation of C. So this is kind of where that curl idea comes from, and why we would care about that. And it also highlights why we can get a sense of the fluid flow just at the boundary, and then it's independent of the surface. Okay, so what I want to do now to close out is just show you some formulas that emanate from the physics world and see if we can unpack them a little bit with our new found language of Stokes' theorem. So here we have Maxwell's equations. These are represented differently depending on what notation you're looking at, but a lot of these follow directly from Stokes' theorem or in conjunction with the divergence theorem, which we're looking at next time. And so you should be able to start parsing these symbols and understand what's happening here. So I'll leave this link in the notes for you to really kind of pour through should you be interested in these applications. There's nothing holding you back from understanding the integral forms of these equations. Okay, I'm not going to have any problems necessarily based on these, but I just wanted to point to these directly as for those of us moving on into physics, electrical engineering, anything of this sort, these are going to be huge. And these are, heralded as some of the greatest equations that the human mind has created. So it's worth a peek in. I'm not a physics guy. I'm a math guy. I live in the pure and theoretical, but I have an obvious appreciation for the language of mathematics shining through and pointing to these deeper truths of reality that have been understood and upheld for about 150 200 years at this point. So pretty exciting. So I'll link these in so you guys can check that out. But again, some of these do require the divergence theorem, which is what we're going to look at next time. And that is a similar theme to what we've looked at with Green's and Stokes' theorem, but it's going to be involving triple integrals. And that will be the last topic we cover in the course. So hope you're still having fun, and we'll see you next time.